In early 2025, coding agents focused on one-shot tasks, writing a single function. By 2026, these systems have evolved to handle entire implementation workflows autonomously. We have moved past tools that execute discrete instructions in a few minutes. Modern agents operate as long-running systems, planning and building complete architectures over the course of several days. The fundamental unit of utility in software development is now the multi-agent team. These coordinated groups manage levels of task complexity that were once impossible for a single model to process. This shift has compressed the traditional software development lifecycle. Because agents handle implementation, testing, and documentation in parallel, projects that once took weeks now reach completion in hours. This creates a role inversion for the software engineer. While AI handles the tactical execution of features, the human developer focuses on the strategic architecture that holds those features together. Technical leadership now requires a specific skill, scaling human oversight across multi-agent frameworks without creating an organizational bottleneck. Attempting to feed an entire enterprise codebase into a single AI model exposes the functional limits of current sequential workflows. A processing core attempting to ingest a massive pipeline of tasks eventually hits a context limit, creating a bottleneck where the project stalls. Hierarchical orchestration solves this by splitting the core into a tree. A central orchestrator distributes the workload smoothly across specialized subnodes. The central orchestrator manages the process of task decomposition. It breaks massive objectives into discrete components, delegating them across the hierarchy to specialized agents. These specialized sub-agents handle domain-specific work simultaneously. One screens incoming data, another queries the database, and a third generates documentation. Because these subnodes operate across separate context windows, they reason in parallel. Their distinct output streams then merge back into a single accelerated pipeline. When the platform Fountain applied this multi-agent architecture to workforce management, they cut the time required to fully staff a new fulfillment center from weeks to less than 72 hours. Scaling enterprise software requires this parallelization of context. Raw model intelligence alone simply cannot overcome a strict sequential bottleneck. Reaching true system scale requires moving away from traditional strict request and response loops. Frameworks like AutoGen version 0.4 enable this by using asynchronous messaging to manage communication across the network. This diagram illustrates an event-driven architecture. Agents drop data into visual queues, continuing processing without waiting for sequential input. When one node finishes a task, it triggers a cascade. Data packets fire off, automatically awakening two dormant nodes for security review. This asynchronous structure allows agents to maintain a coherent state over time. If one part fails, the system recovers and continues working. Applied to a massive codebase, multiple agentic probes navigate the terrain, extracting vectors and mapping the legacy architecture over 7 uninterrupted hours. During these sessions, agents execute an autonomous loop. They plan their approach, iterate on the code, recover from compilation errors, and refine the final output. To maintain stability, these multi-agent interactions rely on strict type checks at build time. This ensures that data passed between specialized agents remains robust. The network even supports full cross-language interoperability. A specialized agent built in Python can seamlessly exchange data with an agent built in .NET within the same workflow. An asynchronous, event-driven design provides the technical foundation needed to turn AI from a discrete tool into a comprehensive, autonomous system. This data reveals a gap in how developers actually work. While AI is used in 60% of tasks, engineers report being able to fully delegate only 0 to 20% of that work. This low delegation rate is a necessary feature of high-stakes enterprise architecture. Effective integration requires active human supervision and validation. Sophisticated agents manage this through intelligent escalation. They are programmed to recognize boundary cases, flagging areas of uncertainty, and pausing for human judgment. Monitoring these complex networks requires advanced observability tools like workflow tracing and open telemetry. On this dashboard, glowing tracing lines track an agent's logic, showing exactly how it interprets tasks and generates output. When a tracing line hits a boundary case, it turns orange and fires a direct escalation ping to the human supervisor dashboard. This new dynamic creates the full stack evaluator. Engineers use AI to fill specific knowledge gaps, allowing them to evaluate entire systems, from front-end interfaces to deep database structures. The human's primary value shifts to applying deep organizational context, subjective taste, and architectural judgment that models cannot replicate. Continuous human-in-the-loop training creates repeatable, reliable workflows that permanently improve the agent network's baseline accuracy. Reaching enterprise scale means focusing human attention exclusively on high-value system validation and strategic oversight. Compressing the software development lifecycle from weeks to hours radically alters project economics. Faster time to value improves the return on investment and makes previously unviable projects feasible. Organizations can now systematically eliminate decades of accumulated technical debt. They assign long-running agents to work endlessly through backlogs that humans never had the time to address. These capabilities are expanding outward. Domain experts in legal and operations are building their own agentic workflows to automate tasks without writing a single line of code. But this technology introduces a severe dual-use risk. The exact same capabilities that harden enterprise defenses allow threat actors to scale their attacks. In this simulation of machine-speed cyber warfare, two digital waveforms collide and counter each other. Automated agentic defense systems are now required to detect and respond to autonomous threats faster than any human operator could. Organizations must bake agentic security defenses directly into their system architecture from the earliest stages of design. The market gap between early adopters orchestrating multi-agent frameworks and late movers relying on single-agent tools is widening rapidly. The defining competitive advantage belongs to organizations that successfully fuse human architectural judgment with the raw execution speed of multi-agent orchestration.